Okay, this is a continuation in the series of EPICS classes, and today we're going to talk about writing drivers for area detector. This is the first time I've given this class, and the plan is this morning I'm going to give. There's really only about 10 slides of an overview of how to do it. And then we'll go through a few specific drivers. I've got three that are sort of rather different that I've chosen that we'll go through the source code and look at them, see how they work. Depending on, and then the plan is for the hands-on part, which is scheduled to be after lunch. What I've come up with is a simplified version of the SIM detector, which I wrote last night. And then I made a version of that that's got only comments in it, effectively, that like we did for the exercise with ASIN port driver and the new port XPS. So you would start with that blank template and start to add meat to it so that it actually does something useful. But if the morning part doesn't take as long, doesn't take all 2 hours, we could get started on the lab this morning if you're interested. So let's see how it goes. And of course, feel free to ask questions anytime. Particularly, this is going to be probably even more informal than the last one. So just chime in if there's anything you don't understand as we go through particularly the examples. Okay, so this is kind of obvious stuff about what I would recommend that you do if you're tasked with writing an area detector driver. The first, of course, is to study the vendor API documentation, because that's what you've got to understand how their API works in order to write an area detector driver to interface to it. Typically, the vendor will provide you with a GUI application that will run, maybe it won't run on the architecture that you want to run on. Often they provide a GUI that only works on Windows, but you want to write a Linux driver. But at least you can use their GUI to understand how the camera actually works and what features at least they've exposed, which is typically all of the features, exposed in their application. Sometimes, if you're lucky, the vendor provides a simulation camera that uses their API but doesn't require real hardware. That's rare, but there are a few examples of vendors that do that. Andor did for their cameras. Photonic Science Limited does for their cameras. So if you're lucky, you have that. So then you can start writing the development even before the hardware arrives, or somebody else is using the hardware. You can still start writing your driver. The next thing, and very important, I think, is to find an existing area detector driver to use as a model. And you want to spend some time to figure out which of the existing drivers is probably the closest match to the driver that you need to write. The differences we'll get into are, how do you communicate with their API? Is it a C or C++ API, or is it a socket library? That splits right there what kind of existing drivers you ought to be looking at. And then if it's a C or C++ API, does the vendor implement a thread that does the acquisition, and then you provide a callback function so that when it's acquiring, you just get called back? Or do you have to basically poll to see when the next image is available and then call some function to get it? And is that function a blocking function, or do you have to check the status and then call it? And it'll return an error if there's no image yet available. Most vendors will write an API, write a library that works on all their cameras. I mean, that saves them effort, right? That there's just one library. An exception, and there are exceptions, is, for instance, Andor has a family of CCD cameras, and You talk to that with version 2 of their SDK. Then for their scientific CMOS cameras, like the Andor Neo and Xyla that are used at Sector 32, there's one in the detector pool, that's version 3 of their SDK, which is completely different. And you know, that's probably historical because they wrote an SDK that didn't use the best software engineering practices for their, and they haven't upgraded their CMOS from that, and then they wrote a better SDK that works with the CCD cameras use the old one, the CMOS cameras use the new one, and you know, I wish they would rewrite make the new SDK work for all their cameras, but that's a lot of work, and I understand that they probably won't. Some other examples, like for the Prosilica cameras, which is now AVT, the library that we're using in AreaDetector only works for their GigE cameras. They have another library that works with their FireWire cameras, and that's old. And now they've come out with a new library, which we haven't started to use in AreaDetector yet, that should work on FireWire and GigE and USB 3. Our motivation to use it will only come when they actually release USB 3 cameras that we want to use, because the GigE is adequate. The library we're using is adequate for GigE, and the FireWire, we have a couple of other solutions because FireWire cameras are very generic. So you can use vendor-independent drivers for that, and we have them for both Linux and Windows. So it depends is the bottom line. Then, of course, you want to determine what features are most important to implement, or at least to implement first, because you don't want to jump in and try to just make everything work before you get anything working. So, you know, figure out what you need to implement first, what do your customers want, and then, of course, start with a simple version of the driver and add complexity a piece at a time. Sometimes you have to write quite a bit of code to get anything to work, particularly to get images out of the camera. But you know, start with not worrying about controlling the gain or controlling the region of interest and stuff to start with. Just try to get an image out. So I've got a table here that that lists what the existing drivers, how they're interfaced. So the first page here is drivers for which the vendor provides a C or C++ library. And I can just go through this quickly. So you've got the SIM detector, of course. That's it. It's all internal. It's inside AreaDetector. It works on any operating system, and it's an internal simulation interface. The Prosilica cameras, this is their C++, the vendor library. It works on these 3 operating systems, and it's only GigE. Point Grey, they provide a library called FlyCap2, works only on Windows and Linux, and supports GigE, FireWire, and USB 3. Aravis GigE is a reverse engineered library for the GigE Vision specification, and that's a library on Linux called libaravis or something like that, and it's Linux only and GigE only. The Perkin-Elmer flat panel detectors, they provide a library called XISL. It only works on and when I say Win32 here, I don't mean 32-bit Windows. I mean the Win32 architecture. So typically we've done these using the Microsoft compiler. And that's a proprietary interface. It's fiber, but I don't think it's gigabit or 10 gigabit fiber. I think it's something else. I don't think it's Ethernet. Then there's, as I was talking about, Andor. They have their version 2 of the SDK for their USB and PCI cameras, Windows and Linux. Their Andor 3 is their scientific CMOS cameras, newer SDK, again, Windows and Linux. And that's, for the cameras that I've seen at least, it's a PCI interface to camera link. They may have now some USB 3 versions of these as well. There's the ADSC detectors, uses an ADSC library, Linux only, and I'm not even sure what interface that is. I don't have one of these.
Fiber.
It's fiber. So it's a PCI card.
Yes.
To a PCI frame grabber to, right. Firewire Win, so this uses a library from Carnegie Mellon. So this is, as I was saying, this is vendor independent. Because this Firewire specification is highly standardized, that's Windows only. Then there's this driver called Firewire DCAM that uses a Linux library, DC1394. That's Linux only. The PVCAM library, for Princeton Instruments detectors, runs on Windows and in principle on Linux. Q imaging, I can't really speak to that. That uses their QCAM library. It's Windows only. Okay, so that's the list of drivers that are in AreaDetector that use a vendor C or C++ library. And the ones that I recall that do callbacks, in other words, that the vendor generates a thread for you, are at least the Prosilica, the Perkin-Elmer, and the Andor 3. Does the Q imaging do that, or they provide a thread that calls you? Okay. Okay, then there's a family of drivers, or a set of drivers, where what the vendor provides is a socket server, and you talk to the camera over the socket. So one of them is the Pilatus. They provide a server called Cam Server. And because they're socket servers, of course, in principle they should run on any operating system. But what I've got for the OS here is what's the OS that the server is running on. So if you wanted to run it on the same machine as the server, which you often do because you want to minimize the network traffic, particularly if you're sending images, then this is the OS that you would use to do that. That's a proprietary interface, the MarCCD. Also, they provide a server here, MarCCD, and you put it in remote control mode. Again, I believe that's a proprietary interface. The MAR345 is an online image plate. It's really slow. It takes like a minute to read out an image. It's an Ethernet interface. The Bruker, they provide a server called the Bruker Instrument Server, BIS. That runs on Windows. Those are USB and probably other cameras from them. And all four of these do not provide a way to get the data out of the camera over the socket. They only write a file, and then AreaDetector has to read that file back to get the data into AreaDetector to be able to call the plugins and so on. The PixieRad is basically inside the camera. There is socket servers, both TCP, which is used for sort of instrument control, and a UDP. And it actually does UDP broadcast of the data. And so you typically want to run it on its own, private cable to a separate network interface. And that's Ethernet. And then finally, there's the PSL Photonic Sciences Limited. They provide a PSL viewer program. This is written in Python, and it's a socket server. And they do send the data over the socket, so you can get the data directly out of the camera. You don't have to go through a file. And some of their cameras, well, I should say some of their cameras are GigE, and for that you don't have to use this driver. You can use the Aravis GigE driver on Linux. So that's what I know. This one camera that I worked on recently for a beamline at Brookhaven. That's what they're doing. It's probably a better driver. This thing's a little lame because it seems to change every week. So it's, they haven't standardized the protocol, although they're trying to cooperate with us to do that. And then finally, there are drivers that don't do either a socket or a C++ library, but rather the vendor gives you an application with a graphical user interface and some way to automate that application. And the two examples that are supported in AreaDetector, they're both from Princeton Instruments. The older one, which is called AD Roper in AreaDetector, uses their WinView application. These both only run on Windows. This one is only 32 bits. This one is only 64 bits. So this is automated, in this case, over the Microsoft COM interfaces, which is sort of an older automation mechanism that Microsoft supports. And then this one uses what's called the Common Language Runtime interfaces. So Lightfield is itself, I believe, I don't have the source code, but I believe it's written in C#. And so it's a bunch of C# objects, but through the Common Language Runtime, you can instantiate, you can call C# objects from C++. You have to jump through some hoops, but it's doable. Once you learn how to do it, it's not that hard. And those are the interfaces they support. So next I'm going to go through some general guidelines and rules for writing an AreaDetector driver. This is all contained in the AreaDetector documentation on our website, although I think I've fleshed it out a little bit here. So in general, as you saw if you took the class on writing an ASIN port driver, your driver needs to implement one or more of these standard interfaces, or one or more of these methods, write int32, write float64, write octet, if your driver needs to act immediately on the value of some parameter. And you would almost always need to implement write int32 because that's where the command to start acquisition or stop acquisition comes over. There might or might not be parameters that you need to act upon immediately on the float64 or octet interfaces. Because for many parameters, you can basically use the base class function. The base class function in ASIN port driver, or I should say that AreaDetector inherits from ASIN port driver, but through two intermediate layers. One is called ASIN ND array driver. That directly derives from ASIN port driver, and ASIN ND array driver knows about ND arrays. So it knows about the generic pointer interface as implementing ND array objects. And then that, in turn, is subclassed by the AD driver base class, which understands some AreaDetector stuff, and that's what your driver inherits from. So it may be sufficient to have the parameters handled by one or more of those base classes and not actually have to deal with a write to some parameter in your driver. Because then what you would do is just when you do need access to that parameter, like when somebody starts acquisition, then you go fetch those parameters, the latest values of those parameters out of the parameter library with get integer param, that's spelled wrong, get double param, get string param, when you need to get them. If you do implement the write any of these methods, then you must call the base class function for those parameters that are not ones that your driver specifically handled, because the base class may need to handle it immediately. So you've got to call, if your driver implements float 64 and you find that the parameter that was passed to you is not one of the ones that you implemented specifically for your driver, in other words, that you added for your driver, then you must call the base class function for that with that parameter. So you have to call AD driver write float 64 or AD driver write octet. And for those of you who were here for the demo when we were doing the area detector demo in the afternoon, you may remember that the HDF5 file writer was not switching where it got its arrays from when we typed into the port field. So it was always getting its arrays from the driver, and we couldn't switch it to the ROI plugin. And the reason for that was that its write octet method didn't call the base class method. And so that was getting, the port that you wanted to use was getting put into the parameter library, but it turns out that the base class needs to immediately act upon that, and the base class was never being called. So those are the kinds of problems you get into if you forget to do that. Of course, if your driver is implementing additional parameters beyond those that are defined in the AD driver base class, then you've got to create those parameters in your constructor, in the constructor for your driver, as we did for those who were here for the Newport XPS. We implemented a few parameters there, and we had to create them in the constructor of our class. In general, your driver is going to need to create a new thread which basically runs the data acquisition task. That thread typically will go to sleep when acquisition is not in progress, and something will cause it to wake up when acquisition starts. It might be, it's often an epochs event that wakes it up. That when your write int32 function detects that, gets a command to start acquisition, then it wakes up that thread. And then that thread would go through and basically, wait for a new frame to come back from the vendor library, and then put that data from the vendor library into an ND array object, do the things that you need to do to add additional metadata to the ND array object, and then call all the callbacks, which will be the plugins that are waiting for callbacks for ND arrays. You don't always have to do this if, as I said previously, if the vendor provides a callback function. So then, the write int32 can just wake up the vendor library, and it starts doing callbacks to some callback function that you've written that does the things that would otherwise be done in this thread, like getting the data into an ND array, and so on. Typically, the acquisition thread is going to monitor the acquisition process and perform periodic status updates, and the details of how you do that are going to depend on the details of the API. If the detector hardware does not support acquiring for a fixed period, remember, one of the things you can do in AreaDetector is say that I want to collect, I want my acquisition time, my exposure time to be 1/10 of a second, but my frame rate to be 1 hertz. So, I collect for 1/10 of a second, but then in that case, I want to sleep for 0.9 seconds before we go back to the top. In some cases, the vendor directly supports that in the API, and so you just implement it there. But if they don't, then you should emulate that in your acquisition loop. And there are examples in the SIM detector, MAR-CCD, and other drivers of how to do that. as I said, the first day, in the first area detector talk, right now, we've got it so that basically the acquire period that says, do we not acquire frames as fast as possible, but rather obey that AD acquire period parameter. The plan is to make it so that that's not always obeyed. It depends upon your acquisition mode. So you can be, if you're in a free run mode, then you ignore that parameter. You just acquire frames as quickly as possible. And only if you're in fixed rate mode does it then obey that parameter. But that's not how all drivers are currently written. And so that's going to be a change. But I think it's a good change because it can confuse users. Okay, and then if the ND array callbacks parameter is non-zero, so you should be able in your driver to turn off callbacks and say, I only want to run the camera, I don't want to call any of the plugins, because that can improve, it can eliminate, for instance, the need to copy data if the user isn't interested in doing callbacks. So if it's non-zero, however, and the driver, meaning the user does want to do callbacks to plugins, then you need to do the following. You have to you're basically setting the metadata in the ND array. So you need to set the unique ID, which should be a unique frame number for each array. Now, sometimes the vendor provides that for you. In the case of the Priscillica camera, the hardware generates a unique ID, or the Point Grey cameras library does the same thing. The hardware generates a unique ID, which is useful because if, in the case of a gigabit camera, you might have lost a frame between the camera and the driver, and you want to know that. You want to know which frame you lost. And if the camera is generating the unique ID, then you want to use that. But if the vendor or the camera doesn't generate a unique ID, then you need to do it in your driver, and in either case, you need to put it into the ND array. Yeah, I would say you do want to increment. If you know that you should have gotten an image and you didn't for some reason, then I would increment the counter. One thing that you should be aware of, and is that in the ImageJ viewer, it doesn't put a CA monitor on the waveform record and generate new frames every time the waveform record posts a monitor. The reason for that is that if you did that, when the user changed the binning, and thus the amount of data that's coming per frame to ImageJ, you would need to change your subscription callback. You'd have to resubscribe to that PV every time the data size changed, which could change when they change from mono mode to color mode or change the binning. So what it does instead is it puts a monitor on the unique ID. And when the unique ID changes, it says, okay, there's a new frame down there. It goes and gets the other metadata about the image. What's the color mode? What's the dimensions? And then does a CA get and asking only for the appropriate number of bytes for efficiency. But if the unique ID doesn't update, you won't get any frames. And that can happen if there's problems with the driver. In fact, it happened with my Point Grey. There's a released version of the Point Grey camera for which this is true if you set a certain value in the startup script. Basically, I was telling because they generate a unique ID in the camera. So I sent the command to them but you have to tell it to do that. It's like optional. You can say here, for every frame it sends you, you can tell it what additional metadata, like a timestamp and a unique ID, it should send you. But you have to ask for it. So I did that, and then, but when you initialize the camera, when you create the camera, the area detector object, you can say, do I want to reset the camera back to some non-volatile RAM settings? And so if you did that, that was done after I had told the camera to send me the unique ID. Right? So now it went back to the non-volatile RAM setting, which said, don't send me the unique ID, and now the unique IDs weren't updating, and everybody's saying, why aren't I seeing any data in ImageJ? So, got to be aware of that. Okay, there are two timestamp related fields in the ND array. The first is a double, which you typically, compute by taking the first. An epoch's timestamp is two 32-bit numbers. One is nanoseconds, one is seconds. The vendor may provide a different one, right? It could be microseconds and seconds or something. So you want to build a double that's based upon the timestamp. And that could be a vendor timestamp, or if they provide it, or an epoch's timestamp if they don't. If the vendor provides a timestamp that was generated in the hardware, you should probably use that. Unless it has some limitations, at which point you might want to make a choice that the user can choose which timestamp do they get. The vendor one, which might only have a millisecond of precision, or the one that Epoch generates, which has got nanoseconds of precision. It's ill-defined, so it probably should be better defined, but with the Prosilica, it's the time since you power cycled the camera. Okay. If it's an Epoch's timestamp, it's time since what the Epoch's epoch. Right? Okay, then there's an Epoch's timestamp also. So this double one is fairly useful because the user can that's something you can directly plot if you've got ND array objects without having to go to a structure, which is an Epoch's timestamp. But we do now have an Epoch's timestamp in the ND array as well, which it's doing from either Epoch's time get current, or you can replace the timestamp function in asyn driver. You want to call asyn ND array driver get attributes. So this will now, your driver can have been given an XML file that says what additional metadata should be attached to every array. And so these arrays will have a linked list of attributes. This goes and gets the current values of all those attributes, which could be from a user-defined function, from the driver itself, or from the last monitor value for an Epoch's PV. And then finally, you want to do callbacks generic pointer so that the registered clients, which means the plugins, get the new values of the arrays. And this is embarrassing, but this is something I need to look into in more detail. But I have found problems of deadlocks when I did that. But I'm releasing the mutex before you call that, and then basically put unlock, callbacks, lock. But I don't clearly understand why I should need to do that. So I need to look into it some more to understand why there would be a deadlock there. A long time ago I found there was, and I have not dug into it, but it's on my list. But for now you need to do that. Or I would recommend doing it, I guess is what I'm saying. There's no harm in doing that because there's no reason that it's okay for other things to happen when that's going on. It's not accessing any class data. Okay, so then the plan was to look now in detail at three drivers that are different. The first is the simulation detector, which implements almost all of the features that are supported that are defined in the AD base class, as well as some that are specific to the simulation itself. Then the MAR 345, because that's a pretty simple socket server example. And then the Perkin-Elmer, which is an example of a pretty fairly nice vendor C API that does callbacks. And then this afternoon, the plan is that you'd write a simple version of the SIM detector starting from a template outline file. But I have a full-blown version of the stripped down SIM detector, the simple one, that you can use for reference as well. And of course, there's the full-blown SIM detector, but that's fairly complicated. That's definitely more than a day's work. And you can go, if you've got your own copy of SIM detector on your laptop, you want to, this is hard to read, you can go look at that. Okay, so let's look first at the header file, which is where the class is defined. So it's, first we got class, Epic Share class, because we want to be able to, if we're building dynamically on Windows, we want this class to be exported from the DLL. Otherwise you can't get at it. In particular, if you want to instantiate it from some other code that's not in this DLL. And then it inherits, it says it inherits from AD driver. That's the base class from which it directly inherits. And I said AD driver inherits from an asyn ND array driver, which inherits from asyn port driver. It's got the constructor takes the name of the port, the maximum size for X and Y, because it does an allocation of an array that big, or it just sets a max. I'm not even sure if that's essential. And then an initial data type for the simulation data. And then all drivers have a parameter, which is the maximum number of buffers, the maximum amount of memory. Now this is, remember, there's an ND array pool from which these arrays are allocated. And you can set limits on that say, what's the maximum number of arrays that pool is allowed to contain, and what's the maximum amount of memory that all of those arrays in aggregate are allowed to consume. And if you put 0, there are no limits. It's just, it's a free-for-all. This is most useful typically on a Linux system. You get a multi-user Linux system, and all of a sudden something goes awry, and you're just consuming, all the memory in the system, and it grinds to a halt. So it can be useful to have a check there. I'm not sure, and it's kind of just a safety thing. It's not, it hasn't been robustly tested to say that if I hit that limit, will it not crash? And that's something to be done as well, because you could wait. If the driver isn't allowed to allocate any more arrays because they're used up, it could wait a little while until the plugins free some arrays and then continue on. But it's more designed just to prevent catastrophic freezing of your Linux box. Yeah. AD driver, yes, and yes, they're in 8. So let me just I can show you the directory structure here. So if we go to in Epic's Devel AreaDetector 80 core. Okay, so in here there's AreaDetector 80 core 80 app. 80 source is where the asyn ND array driver base class is. That's that. It's where the ND array class is defined. It's where the AD driver base class is defined. So it's there. and then plugin source defines a plugin base class and all of most of the plugins for AreaDetector are in here. Some of the ones that have been contributed by other groups that require maybe more, they're not as portable, might not be in here. You know, they're in their own repository. For instance, the FFmpeg server plugin from Diamond is in its own repository. It's not in here.
Should they also just put that in a separate AreaDetector module?
What's that?
Their plugin.
It is in a separate AreaDetector module. That's when I say repository, that's what I mean. So it's right here. It's FFmpeg server is at the same level as all the other drivers and so on. No, it's the only, by putting it this way, it does put constraints on the order in which you would need to build things and dependencies, right? So if you want to use the FFmpeg server plugin from the ProSilica camera, you would need to build them in the right order, right? And make a dependency in ProSilica on FFmpeg server, which hasn't currently been done. So, right. FFmpeg server is a relatively recent addition to AreaDetector, and it's not obviously as well integrated as the other plugins at this point. But if you want to use it, it's not hard to do. It's just you can't do it right out of the box. Okay, so that's max buffers and max memory off, and you set that in your startup script. And a priority and a stack size, that's the same thing you've seen for asyn port driver. That just sets if the thread that gets created both by asyn manager, and it probably should also be done for the thread that's created. If you create a thread here, to use those priority and stack size. But if you put 0, you get default. Well, you should pass them into the base class. Because that's the thread that asyn manager creates for you. And then here are the methods that we're overriding from AD driver. So write int 32, write float 64. You saw these in the other exercise. If you did that, you know, they're just the methods that get called when there's a new integer or floating point parameter. Those are, you know, from way down in asyn port driver. Set shutter is something that is in AD driver. So this is a method that you can implement if your hardware, if your vendor supports a shutter. You should implement that. But there is a base class method that uses an Epix PV to open and close a shutter. So, you know, it assumes that, you know, or it allows you to have an Epix PV that you can control the name of the PV that opens the shutter and the value you write to it to open the shutter, and a separate PV, if there is one, that closes the shutter and a value you write to that, which is what you need to do if you want to use your beamline safety shutter. Because the beamline safety shutters use two different PVs. There's an open PV and a closed PV. Lots of times, if it's an IP Unidigi, it's, you know, binary output record you're using, it's probably going to be the same PV, and you just write 1 or 0. No, this is, as I explained the first day, when we went to GitHub, we completely reorganized it. So you're not looking at AreaDetector 2. You're looking at AreaDetector 191, which is completely different organization. Because what we did was to make these detector drivers be completely separate so that you can build AD core and not worry about any real detectors. And similarly, we can release new versions of the PerkinElmer without having to release a new version of any other driver or any other thing in core. So it's a much cleaner model, but it's not compatible with the old model. The code was taken from the old stuff, but it took quite a bit of work to break up that subversion repository, and I gotta hand it to Michael Davidsaver at Brookhaven. He gave us a lot of help in doing that, because I would have had no clue. Okay, then we got a report function, and now we've got this simulation task that actually does the what I was talking about before. That's the thread that does the acquisition here. And then these are the new parameters that the simulation driver supports beyond those in the AD driver base class. So, we've got some gain X and gain Y and red, green, and blue gain and noise and some peak width parameters and so on. So these are just those parameter numbers. And then we've got some private data here. And you'll notice there are 3 template functions here that take a type name of epochs type. And so there's compute array, compute linear ramp array, and compute peaks array. And we do these as template functions because we want to be able to have them support any data type. And so we write them once, and with this template parameter, they can implement multiple data types. Then there's a function compute image, which is actually going to invoke this, which in turn invokes this or this, depending on which type of a simulation we're doing. Then we've got some epochs event IDs, a start event and a stop event, which is what we're going to send to this task here to wake it up or tell it to stop, go back to sleep, and an enum, which simulation mode we're doing, and then the strings that are what the epochs records use to for each of the new parameters that we're doing, and a little calculation here of how many parameters we're implementing. So that's the header file, and it's a good idea to define your class in a header file, because that way it could be used to instantiate. For the way area detector is typically used, you don't absolutely have to do that because it's typically invoked only from the IOC shell code that's in the same C++ file. But if you want to be able to instantiate this detector from some other C++ code, of course you need a header file that defines the class. Okay, so let's go look at the driver code itself. One thing I just want to say a little bit about here. Now, in this header file, you need includes here that define, of course, anything that this header file needs to know about. In this case, it needs to know what's in AreaDriver.h, because we're saying this is inherited from AreaDriver. And it has down here an epochs event ID, and so it needs to include epochs event to be able to have the compiler know what that is. But I'm doing this for people who aren't familiar with how you need to program for Windows, right? Which has to do with the correct location of epochs export.h here and what needs to come before that. And the critical thing here is that epochs event.h, which is contained, this file, simdetector.h, needs to come after epochs export.h, because that defines the symbols that this module, this library, is exporting, which needs to come after epochs export.h. But and you might have said, oh, well, simdetector.h includes epochs mutex.h, so I don't need to put it here. That's not true. Because if you do that, then it will assume that your library is exporting epochs export.h. So you have to include it here before the epochs export.h, so that the second time it gets included, it's already been included and it doesn't do anything. Right. Is that a good way of saying it here, Andrew?
And including the epochs export.h header turns a switch, which on Windows basically says it switches the meanings of all those epic share things that you see on functions and on the
Right.
epic share
From
I'm importing this to I'm exporting this, which is why epixexport.h is it's really it should be more obvious where epixexport.h is in the include line, but it's not.
right. And I'm including epixexport.h here because I am indeed using some of the functions of epixexport.h down here in the IOC shell stuff, right? Or somewhere. Yeah, this epixexport registrar that's defined in epixexport.h. If you were not doing that, you don't have to use epixexport.h. You can just say include sharelib.h and then define epixexport shared symbols, something like that. And which is the right way to do it. So you shouldn't include epixexport.h unless you really need it. You should just define this other symbol because the epixexport.h does additional stuff that you shouldn't do if you don't need to do it.
Yes, but there's no other way to register the IOC with this name.
Exactly. That's why I'm doing it here, because I need epixexport.h. All right, so that's a little bit of an aside, but I'm always cleaning up code that doesn't have this right because nothing goes wrong on Linux, and it doesn't go wrong on Windows if you're doing a static build. But if you're doing a dynamic build with DLLs on Windows, then this goes wrong. Or now, what have I found? That even if it goes wrong on Cygwin, I think even if you're doing a static build. I think that's right. Right. And you'll get these funny messages that it'll say, Epix mutex is not defined or something, because it thinks it's supposed to be exported by this module, but it's not. Yeah, so in fact on Windows now, there are 8 possible builds, right? You got 32 or 64, dynamic or static, and debug or not debug. Those are, or no, yeah, that's right. Yeah, so it's 2 to the 3rd possibilities. There are 8 different things you need to test. And even if 7 of them work, sometimes the 8th one doesn't work. Because and that has to do with if you're using some library that somebody else gave you, it might work on non-debug but not work on debug, and it can be tricky. Okay, so let's look a little bit more at the code here. So I don't know. I guess going through it, I'm not sure what the most logical way to go through this is. Maybe we should start in the constructor, which is illogically down. So this is just the IOC shell stuff that defines the command. And what that does is it calls this function SIMDetectorConfig, which has got extern C because it needs to be called from the C code of the IOC shell. It just says new SIM detector, so it creates a new SIM detector object, which of course invokes this constructor here. And so the constructor, first thing it does is invoke the AD driver base class. It tells it the number of addresses that this is going to support. Most drivers, detector drivers for AreaDetector would only support a single address. If for some reason you wanted one driver to run multiple cameras in one instance of a driver, which I can't imagine why you would do that, but maybe you would, then you might need to support multiple addresses. What the first address 0 talks to the first camera, address 1 talks to the second camera. The number of parameters in the parameter library, and then we're just passing max buffers and max memory. This is that interface mask, what interfaces is this driver supporting? And the base class already says that it's going to support int32, int64, driv user. So usually, unless you're doing something unusual, you can just put 0, because the masks get ORed together. So you can just put 0 for these masks unless you're implementing some other interface. And then this is the flags. This is the SIM detector. So we've set can block equals 0 because it should be fast. But most drivers would need to set this to 1 because when you make a call to your vendor API, it's not going to be fast. So you need to set the can block flag. And we've set it to auto connect. Initialized some pointer here to null. And now we call epics event create to create the start event and the stop event. Create all these parameters with the appropriate data type and a pointer to the that parameter integer. And then you might want to set the default values for some parameters so that it comes up in a reasonable default configuration. Remember, at least if when the IOC starts up, the output records will go ask the parameter library for the value of that parameter. If they get a successful response, then the output record will take that value as its initial value, and they will get, with ACE import driver, that will generate a successful response if you have set that parameter in the library with a set integer or set double or set string param. If you've created the parameter but you haven't initialized it, then that read operation will return an error and the output record will not get set to that value. So this is a useful way of having the parameters come up with a default value. Even if the IOC's never been run before, these will typically get replaced by what's in save restore once the IOC has been run at least once in that IOC, in that same directory. It's not to stop the IOC, it's to stop acquisition. Okay? So we'll see when we go look at the task what that does. So we set a bunch of values for the parameters. Then we call epics thread create to create the simulation thread. And that's it. So that's what happens in the constructor. So now let's go see what happens when we turn on acquisition. So that's implemented here in the write int32 method. So this code up on top here is some stuff that we could probably ignore. I mean, what it does is there's a status message PV, and so when you should probably update that message to reflect the current state of your driver. So this is basically the code up here is just updating that acquisition status. And the next thing it does is to set the value of the parameter, whatever it is, in the parameter library. And if the function is acquire, so this is turn acquisition on or off. If value, so value is the value of the parameter passed in here. If that is non-zero and we're not already acquiring, and one of the first things it did up here is get integer param ad acquire acquiring, which is an integer. So it's basically one of the first things it did when it came into this routine is to ask, are we currently acquiring? And so if this is true and we're not currently acquiring, then call epics event signal start event ID. So it's sending a signal to that computation thread, to the thread that is generating the images to start. Or if value is false and we are acquiring, then send a stop event. And then if the parameter was data type or color mode or simulation mode, if any of those happen, we basically have to reset the image. And because the way the simulation works is that it generates an initial image, which is computationally intensive, and then each time it generates a new image, it just modifies that image. And but if you've changed the data type or other things, then you need to reset the image and start over. So it sets a flag saying we're going to reset. Call the callbacks to the higher level, print out some error or success messages here. So that's all there is to it. We can just look at write float 64. Again, it's saying if you change any of the following parameters, then you need to recompute the base image. So if you change the time or the gains, blah, 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 you just set the reset image flag. And then you notice else, if this parameter belongs to a base class, call its method. And this one, the integer does the same thing. So if the function is less than the first sim detector param, in other words, it's not one of ours, then call AreaDriver write int 32 or call AreaDriver write float 64 so that it's properly handled by the base class.
I noticed, Mark, there that you don't allow the case that a parameter might be larger than yours, i.e. somebody else might derive from this class.
But they would have been called.
They would have already been called.
They're called first. So they better call me, I don't call them.
Okay. Right.
So wait a minute, where does that number come from, which is the lower limit on your parameter?
First detector param?
Right, yeah, is that grade param that gives you that?
It's from the header file.
How can it be in the header file? How do you know what's, you know what's in the base class?
Mark, pull up the
Yeah.
.h file.
Right.
Those two macros.
Right.
You don't know the value of them.
I don't know the value.
You don't know that. So you're going to get the value of that from create param?
Yes. So the value of sim gain x is determined at runtime by create param. Right. Right. Okay. So now that was right in 32, and this is the simulation thread. So this is SimTask, the thing that we did Epic's thread create. So we come in, we take the lock. So now when we enter this loop, we've got the lock. And we say, if we're not acquiring, then wait for a semaphore that's given when acquisition is started. So if not acquire, prints a message here with asyn trace flow. So if you've turned on asyn trace flow, you'll see a message that says waiting for acquire to start. It calls unlock and calls Epic's event wait start event ID. So it's just basically waiting here for somebody to press the acquire button. As soon as they do, and this is not done with Epic's event wait with timeout, it's waiting forever. Which means that this thread would never clean itself up on Epic's exit. So you could think about whether that is how it should be done. But at least it's not going to be accessing some resource that disappears during cleanup, Epic's thread cleanup. Unlike what we saw with the XPS the other day, where we were polling something and then the socket went away and we started spewing out error messages. So we unlock. As soon as we get the event, we take the lock. That means nobody else can be calling write integer param, basically all the Epic's records are locked out of calling the driver right now. We set, this is just a local flag, acquire equals 1. We set a message that says we're acquiring data. We reset the AD num images counter to 0. We go get the current time, which is the start time for this image. We get what mode we are in. That mode is going to be single frame, multiple frame, continuous. Get the exposure parameters, the acquire time and the acquire period. set our status to status acquire. That'll make a message appear on a screen. You know, a PV. No, that's just a MBBO record. Open the shutter. So you call set shutter, AD shutter open, and you will find that set shutter is not implemented. Well, no, I guess it is implemented in this class. It said it was in our header file. I'm not sure what that does. Okay, then it calls the callbacks because you've changed some things here. This would let the user immediately on their MEDM screen see whatever has changed so far. Then what it does is simulate, and you know clearly this isn't what you do in a real detector, but this simulates being busy during the exposure time using Epic's event wait with timeout on the stop event. So it's going to wait for the acquire time, but if you press, you know, the user, if you accidentally typed 600 seconds for the exposure time, you could now stop it. You know, it wouldn't sleep for 600 seconds. As soon as you press the stop button, it'll, and you notice it's unlocked here, so the Epic's PV, the Epic's record, would be allowed to process and tell the acquisition to stop. As soon as it gets out of this wait, either because the acquire time has expired or somebody's aborted the acquisition, it takes the lock.
Is that lock in this class, or is that from the base class?
That's from ASIN port driver.
Oh.
Yep. Yeah. Although, I mean, you could re-implement it, but I've never seen a need to do that. I guess this is saying if the acquisition time is 0, it'll do Epic's event try wait. I don't remember why I did that. And then if it was Epic's event, if the reason that this terminated was Epic's event wait OK, which means that the user pressed that it did get the stop event, then it says, oh, somebody told us to stop. We're going to set the acquire flag to 0. If we're in continuous mode, we set this to idle, else we set it to aborted. This was some stuff that the Diamond guys did to, you know, they wanted to make this, you know, have nice status information. Okay, so then here's the critical step. It says status equals compute image. That's where we're going to generate the new image. And then close the shutter, and we'll go look at the compute image in a second. If we're done acquiring, continue just means, you know, go to the end of the loop there. But if we're not done acquiring, well, I think that probably means we aborted acquisition. That's right. Set the status to readout. Okay, now it's p-arrays 0 is something that comes from ASIN ND array driver. So basically, there's an array of ND arrays, and we're getting the first one. That's where we're basically storing the current image is here. And it's done that way so that the base class, if somebody goes and does a read on an image, the base class can handle that for you. You know, you've got a pointer. As long as this is a non-null pointer, the base class knows that there's an array there that a waveform record could read, or somebody could read, not a waveform record. Okay, get the current values of the, okay, so this is basically going and getting a couple of counters, incrementing them. One is the counter that basically started at 0 when the IOC was created, and another is the counter that restarted when we started this acquisition. So then we put the image counter, that's the global counter that started at IOC init, into unique ID, set the timestamp here from the start time of that acquisition, update this timestamp, get any attributes that have been defined for this driver. Okay, so this is, you know, get attributes. You pass it the attribute list for this image.
generated when somebody hit a board?
What?
Post a new image after you hit a wall.
So
It doesn't post a new image, so it doesn't update it.
So the unique ID is not updated when somebody kicked a board.
No, not in the SIM detector.
If it's continued before, is the unique ID is,
Right.
is it the right thing or?
Because you're not actually you're not posting the image.
You're not posting, yeah. So if you hit a board, it's not executing any of this code.
Yes, it is, but I think that it should because the image started already. Yes, or
Yeah, you could argue that it did compute the image.
yes, it is.
So we could have argued that should have skipped this step. If you aborted, don't compute the image.
Okay.
Move that, continue up a little higher. Okay. So this is getting the attributes, the current value of the attributes, and then if array callbacks, which was something we went and read whether that was with a get integer param right here. So are we doing array callbacks? If so, do callbacks generic pointer with this image. This is the the reason field that we're doing callbacks for. Unlock, lock. So now that's called the plugins here. All the plugins have all been called with this single call here. Now we see, is acquisition done? And this is the kind of thing that you may need to implement in your driver's task here if the vendor doesn't support this. So, if we're in single acquisition mode or we're in multiple image mode and the image counter is now greater than the number of images we're supposed to collect, then first do a callback on the status, set it to idle, call the callbacks, acquire is set to 0, set that, and then say acquisition completed. I'm just printing a message here. But the important thing is that you not set AD acquire back to 0 and do the callbacks until you've called the plugins. Because if one of those plugins is set to blocking, remember AD acquire here is a busy record. And so if one of those plugins is set to be blocking, you want to guarantee that the code in that plugin executed before you set the busy record back to 0, because that's what the scan record's going to be waiting for. So you want to make sure that the plugin has executed its code before you let the scan record go get the data, basically. Yeah.
So you're using one key image, and then you're passing it to the plugin, and then so you get another image. How do you know that the plugins are done that data before you start writing to that key image again?
Because we haven't gone and seen compute image. Compute image is generating that P image, and it's doing it with ND array pool. It's getting a new image out of the pool.
Okay, so you're doing like a release and
Yes, but that's done up in the compute image code.
is there a way to tell if the reference count on the images? So if I want to reuse the same one instead of
That's transparent to you. So as soon as the plugins, each time you call a plugin, it increments the reference counter. And now in their threads, when they're done, they call release, which decrements the reference counter. And as soon as it goes to 0, that's done with a call to the ND array pool class. As soon as it goes to 0, it's back in the pool. So you will reuse that image, but it's transparent to your driver.
okay.
It's just ND array pool alloc will give you one that's free. The next one it can find that's free.
So set integer param, does that necessarily process the record, or is
No, it never processes the record. It's only call param callbacks that would cause IO interrupt scanned records to process.
Okay.
And that call param callbacks guarantees that it will call all your set integer, all your set x param things in the order in which you set them, yes?
Yeah, I've never thought about the order in which those are done. I believe yes, I believe in the param list class, every time you call it, it sets the does it set a flag or does it set a number? I think it sets I think there's an array of the number of parameters in that list of changed values. And so when you write to a parameter, if it's changed, it puts index 1 as the first element in the changed, or index 10 as the first element in that array, and then it goes through that array and calls them. So I'm pretty sure you're right that it would call them in the order in which they were changed, but I never rely on that. I rely on not calling call param callbacks until I'm sure I want that to be called. So I already called it up above for everything else.
Cleared everything else.
That's right. It got called here. First of all, yes, I called it here, then I set this and called it again.
And that will actually cause the record to process only if the record said, I want to be processed when this thing, right? I mean,
All it does is call scan.io request, right? And that actually happens in another thread, doesn't it? Yeah.
Triggers a callback thread.
Yeah, that triggers it. So there's no.
so it's the database that makes the decision of whether the record actually gets processed by the setting of the scan field.
That's right. It only processes, scan.io interrupt records. Other records, periodically processed record is just coming in and calling readInt32, which is implemented. It's not implemented in this driver at all. It's implemented in the base class, and it just gets the last value out of the parameter library. Okay, and then this is again with our simulation. So if we're acquiring, then sleep for the acquire period minus the elapsed time. So I figure out, how much time has actually elapsed since the start time. And if that's, and then a delay, which is the period minus that. And if that's greater than 0, then sleep, epochs event wait with timeout for that delay time. So we're trying to run at 10 hertz. Even if the exposure time was 1.5 seconds, this should sleep for approximately 8.5 seconds. But it tries to be more accurate than that because it's based on how much elapsed time has actually happened rather than just the theoretical time. And then again, at this point, the user could have also pressed abort, right? So again, you want to set acquire to 0 if the user pressed abort here, and do the right things. All right? Okay, so let's just go take a look now. The last thing really is compute image. Let's see where that is. Right, okay, so this is compute image. This is the thing that's directly called from the simulation task. It goes and gets a bunch of parameters, that describe how we're going to do the simulation with binning and reverse and data type and so on. Makes sure the parameters are consistent so that, if you've asked for a binning that's less than 1, but this should really be handled probably in a driv high and driv low field. But if you've asked for a minimum and a size that is bigger than the whole array, so it's basically trying to make things legal here. And then because we're implementing different color modes, we've got some indices we need to worry about. The number of dimensions, which dimension is the color dimension, which dimension is the X dimension, which dimension is the Y dimension. Which is different for RGB1, pixel interleave, row interleave, plane interleave. Then here's the question about the allocating of the buffer. So if reset image is true, and it did that, remember we were calling set integer param on reset image. It goes and fetches the value of reset image and and says, okay, if reset image is true, then we can't use the previous raw buffer because it's not the right size or the right data type or something. So it frees it. It calls praw release. Then it says dims of x dims equals max size x, dims of y dim equals max size y. If the number of dimensions is 2, greater than 2, then the color dimension, blah, blah, blah. And then it goes and calls nd array pool alloc, the number of dimensions, which is either going to be 2 or 3, an array of dimensions, and a data type. And then nd array pool alloc can take two other arguments, and I believe these are the size that it should allocate, but if you put 0, it allocates based upon the calculation it would do on the data type and the dimensions. But you could ask it to allocate a bigger buffer than that if you wanted to. And then this is a pointer to the data array. So if you've pre-allocated an array somewhere, you can pass a pointer to that here. But typically you don't. And then it will go and get, so this will go look in the pool and try to find, what it does is go through, the pool is a linked list, and it goes through and tries to find the first ND array in that pool that's big enough to satisfy, whose buffer is big enough to satisfy this request. But if it's bigger than it needs to be, it doesn't free and reallocate. It just says, hey, that buffer's big enough, we'll just use it. So that makes it efficient. If you started with your detector unbinned, and then you binned it and you only need arrays that are smaller, it doesn't free them and reallocate them. It just says, that's big enough, we can do it. And then if you unbin it again, you're back to having arrays that still work. And only if it goes through the whole list and doesn't find one that's big enough, then if it hasn't hit the limit of the number of arrays that are allowed to be in the pool, it'll create a new one of the correct size. If it's not allowed to create a new one because you've already hit that limit, but there are free ones in the array, it'll go through and delete and take one of those and reallocate the buffer so that it's big enough. So it works pretty hard to try to not reallocate memory. It also, by default, doesn't, when you put it back in the pool, it doesn't free the linked list of attributes. And so when you get one out of the pool, it'll already have that linked list of attributes.
In that part, is ND array pool is created when the IOC starts, or?
Yes. It's ND array pool alloc is when in our constructor down here, we called the constructor for AD driver, and we passed it the maximum number of buffers and the maximum memory that's related to the ND array pool. AD driver doesn't implement that, but asyn ND array driver, the second class down, creates that pool for you and handles that ND array pool.
So in the st.cmd, those numbers should be set. Yes.
But I would normally, yes, they should be set, but you can typically set them to 0.
Oh, 0 means?
0 means there is no limit, because it doesn't pre-allocate anything. This is just a limit. It allocates on demand, but this limits the maximum that it's allowed to allocate. But if you set it to 0, then there's no limit. But if you have well-behaved code, that's fine. But if your code goes awry and you forget to release, you do an ND array pool alloc and you forget to have a matching release, then your memory consumption just goes up and up and up and up. And so probably when you're debugging, it's a good idea to set these to a value, and then when you're done, to get rid of those. I mean, that's one way to do it at least. Okay, let's go back up to the simulation task. Okay, so what? Yeah, this is compute. That was, oh, I'm still in the wrong one. This is compute peaks array.
I think it's above.
No, I think it's this one, compute image. So compute image, so compute image is private. And it's only called from that one place in the simulation task. So we freed the buffer, we allocated a new buffer. If we couldn't allocate a buffer, we just print a message and return, but hopefully that never happens. And then we've got a switch here on the data type. So we've got 8 possible data types, and what those do is just call compute array passing the data type and the maximum size in X and Y. And then, so compute array, again, is where the real work is done. But let's assume, we'll go look at that in a minute, but let's assume that that worked. So now we say, so what that did is it computed an array of the full size of the image, whatever you initialized it to in the constructor. And now the binning here is actually done in software. So it takes the array that you compute and then bins it in X and Y. And so let's see, how does this work? Initializes the dimension. All right, and it calls a init dimension, which is a method for in the ND array, and creates a dims out. The point is here that we're calling ND array pool convert. And this is a very powerful function. So basically, it takes one array and converts it into a second array. And it can do, in the process of doing that, it can do a number of transformations. It can bin, it can reverse the indices, and it can change the data type.
This is not image graphics method.
No, this is something I wrote that's in ND array pool. And it's fully unlimited in how many dimensions it can do. So it's recursive code over the dimensions. It's the most difficult 50 lines of C code I ever wrote. And don't ask me to ever understand it again, right? But it works, and it's very efficient, right? So it goes through, and in this case, we're using it to do binning. But you can use it to do lots of things, convert from one data type to another, reverse the indices, extract an ROI. So this is, it goes and you can give it the minimum and maximum in each dimension. And so it can go extract an n-dimensional ROI out of an n-dimensional data hypercube or whatever you call it. That, it doesn't do color conversion. Right, I don't think it does. I don't remember. I don't think so. Because the color convert plugin does that, doesn't use this to do it. Okay, so, and you notice I'm passing, so this p raw is the input, and the address of p arrays 0 is the output. So it's going to create a new ND array and stick it in p-arrays 0.
Do you ever use anything other than p-arrays of zeros? That's the only one index I've seen you use on p-arrays. Any other
I think if your driver was multi-device, there would be n of them. And yeah, and so the original implementation of the ROI plugin, which supported multiple ROIs in one plugin, did that. And I haven't looked to see if Matt Pearson's new plugin that's called ND ROI Stat does that or not. In fact, I haven't looked at his plugin closely enough to know, does it actually export arrays or does it just do statistics? I'm not sure. I think he probably just does statistics. Yes, so it does the conversion. So that does whatever binning and reversing directions, because that's something you could do in the SIM detector, and converting the data type. No, the data type would always be the same, I believe. But other plugins use it to do the data type. Then it says p-image is p-array 0, calls p-image get info. So this is a sort of a utility method in the ND array class, fills in data in a structure. One of which the one that's used a lot is that it returns array info.total bytes. So it tells you how big is the data that is actually occupied by this array, as opposed to how much data is allocated in the ND array, which might be more. And so this is setting some integer parameters, the dimensions that will be epochs PVs that you can see how big, because if you binned it, now this tells you how big is the binned image. And then it sets reset image to 0 because we're all done and returns. Okay, so let's go look at the template classes here. The first one is very simple. And we won't. Okay, so the first one is whatever our function what I just looked at was compute image, right? It called compute array for each of the possible data types and passed it an x and a y size. And then this method simply goes and figures out which simulation mode we're running, linear ramp or peaks, and then invokes that template function with the same epochs type and passing it the dimensions. So this is the one for compute linear ramp array. And again, it's a template function, takes this type. That type is used in a few places like epochs type, increment mono, red, green, blue, and pointers to the mono image, the red image, the green image, and the blue image. Or data, I should say, not images, but the data. And so it goes and gets some parameters, and then the intensity of each pixel is given by this expression, and does some intermediate calculations here, and then basically goes through, figures out, as we did before, depending on which color mode we're using, where the pointer to the red data, the green data, and the blue data is, and what basically what the stride to go through the array to get to the next pixel is in all of those dimensions. And okay, so if we are resetting the image, this does the calculation of generating the initial image. Else, this does basically the increment of down here rather. It's doing an increment of the image, which is faster. And that's basically it. And then this is similarly, if it's an array of peaks, these are a bunch of Gaussian peaks with noise. And that's just the calculation to do that. It's a bunch of code, but there's nothing very, very innovative or anything that you need to look at about it. Okay, and this is Okay, so this was just showing sort of how you would implement a shutter. In this case, it's saying if the shutter is shutter mode detector, so there's a shutter mode detector and a shutter mode epochs. If it's shutter mode detector, then it's basically just simulating a shutter here. But if it's either no shutter or an epoch shutter, call the base class method. So the AD driver base class method is what implements an epoch shutter. Or if it's no shutter, it does nothing. So your driver should do this if your vendor supports a shutter. If not, just ignore it, because the base class method will be called. Okay. Where are we at here? Oh, it's almost noon. Okay. Let's just quickly look at the MAR 345 driver, because I don't think it doesn't take that long. Because a lot of it's going to be similar to what we just looked at. Okay, and here I didn't follow my own advice of putting the class definition in a header file. So it's all in the C++ file yeah. So we couldn't have instantiated this from another.
The only way of instantiating it is by calling your constructor function, but that's probably the way you want people to do it anyway.
But don't I need to export a header file so that I can say what I'm making a class of?
No, because you can just declare that as a class.
I can just declare it as a class. I see. Okay.
So shouldn't you not be exporting async object sync IO? Based on what you were saying before, is this written?
Exactly. Exactly. And I haven't discovered this problem because I can't build this. I don't build it on Windows, right? But I could build this on Windows because it's just a socket client. So good point. That's right. The epochs export here should be the very last thing because there is no header file that defines its own stuff. So it should be the last thing here.
MAR 3XX header is probably for some other function that might go into this library, or is that?
You are right. That goes, yeah. So it's not just what's this class, it's what goes into this library that needs to come after the epochs export. Right. That is definitely in this library. Okay, so what we've got here is just some constants because we're going to be passing messages. So we're defining some maximum message size and some timeouts, some poll delay. There's some trigger modes here. AD driver defines some trigger modes, but this uses a different set of trigger modes. We're defining an enum that says with the MAR image plate, what you have to do is if you don't know how these things work, it gets exposed to X-rays. It puts the phosphor into an excited state, metastable excited state, and then when you're done exposing, there's a laser. The thing spins around, and there's this laser that goes radially outward like a record player. Shines some light, stimulates the phosphor to go back to the ground state with emission of a different wavelength of light, and you count that. And that tells you how many X-rays hit there. But then when you're done, you also need to erase it. So there's another laser, a higher powered laser that goes through and basically puts everything back to the ground state. So you can control when do you erase it. You erase it before you collect an image or after every image or never. So that's this thing. And And then you can read it out at different resolutions. 100, I guess this is, or maybe it's a different diameter. I guess that's what it is. Yes, you can say I don't need to read out the whole plate. I just, my pattern's only in the middle. So I read out 180 millimeters or 240 millimeters. This is the resolution, 100 micron or 150 micron. And then, some status states, basically, defining some states that we can be in. You definitely want to give the user feedback here because this thing takes a minute or 3 minutes in its highest resolution. So you want to give them some so these are the parameters we're implementing that are new: erase mode, number of times to erase, the size and the resolution. This is the definition of our class. Just like we saw before, we're implementing only write-int32. There's no need to implement write-float64. We're implementing a set shutter. This thing does support a shutter. Report, we got start event, stop event. In this case, I also made an abort event because the task is probably implemented somewhat differently. And these are those, just the private, the data for those parameters. Then we have some private methods: read a file, write to the server. That is the socket server we're talking to. Read from the server, erase, change mode, acquire frame, read out a frame, wait for completion, some private data. We got a message, defining a message buffer here, the string to send to the server, the string to read from the server, P data, that was like P raw in the last one, an ND array, that's private. And yeah. So yeah, get image data here is, remember this thing can't send us data over the socket. It just writes a file. So I think this is, yes. So this is going and figuring out how big are the arrays going to be based upon the dimensions. Then it calls ND array pool alloc. That's to a local P image here. Hopefully this is all done right. So it allocates an image saying it's always going to be two-dimensional. It's always going to be a 16-bit unsigned integer. And now it calls fopen. So it's figured out what the full file name that the MAR image plate wrote to was. So now it's trying to read, and it reads that file with this function called getPCK. So this is a function I think that we got from MAR because these things are compressed files. So they gave us the code to read this file. And then we close the file, put the unique ID into the image, put the timestamp into the image, get any attributes, call generic pointer. And then it just calls pimage release. So it's just freeing it right here. It's not saved a local copy of it, right? So it's the P array 0, and it probably should have, is there so that if somebody calls read generic pointer, then there's a place that the base class can return an array. I don't think that that's used very much. I don't know that it's used at all, that anybody's ever calling the read generic pointer.
Lets you always read the last image.
Exactly. The last image is sitting around and you can read it. But I don't know under what circumstances that actually happens. I can't think of any. But it's there in case you want to do it. So this is just a function to the write to the server. So this is using, using the asyn octet sync IO interface. So the write goes and does a flush because it's likely the next thing is going to be a read, does a write, and with some timeout here, And then what I do here is to set whatever string we set, put it into this. There's actually a base class parameter which is called string to server, or AD string to server, because this is pretty common, right? And you'd like the user on their MNEM screen to see, to be able to look at the communication, or do a CA monitor even on the communication, see what happened. So you can see what's going on. Read server is similar. It's just calling pasyn octet syncIO read, seeing if it worked, setting the string that it got back to a PV so that you could look at on the screen. This is a wait for completion function. Yes, okay. So basically this thing is just polling the server, and until it gets, the response it gets is the done string, which is passed to it. Because you can tell it to erase, and then there's a certain string you wait for that says I'm done erasing, and then you say acquire, and there's a certain string you wait for that says I'm done acquiring. So that's just encapsulated here in this wait for completion. It just reads the server, waits for, and there's some timeout here that's being implemented. Where is it? How does it do it? Oh, if the elapsed time is greater than, okay, so this is a timeout. It's saying, I'm going to wait, I'm going to poll it periodically, but I'm only going to wait 60 seconds or whatever for the response to finally come back. And if I don't get that response, I just return an error here within the timeout period. This is something that does, changes the mode. So it goes and figures out what mode does it want to be working in. This is like the diameter and the resolution. And then it builds a string here with epix sn printf into this to-server string, command change, and then %d, which is some number based upon the resolution and the size. There's an array that was defined up at the top. Then wait for completion, mode change, ended OK. So I'm waiting for that string to come back. And like I say, these things can take minutes. This is erase, which is basically doing the same thing. Command erase, and then wait for completion, scan data, ended OK.
Mark, is done, which you had before, is what kind of string?
Which one?
The done.
It is this string I'm just showing you. So this done string here, in this case, is is mode change ended OK. That's the done string. In this case, it's scan data ended OK with some number of spaces in here. Right? And hopefully they don't change the syntax. Here's the set shutter. Yes. So if we're in shutter mode detector, we write to the server command shutter open, and then this is actually implementing an epix thread sleep, and then for that delay, or if it was a close the shutter. Oh no, this is implementing, is there a delay between when you tell the shutter to open and when it actually opens? And it's waiting for that delay here. So that when this function returns, you can be sure the shutter is actually open. And then similarly, command shutter close if you were told to close the shutter.
So this is not a variable?
What's that?
The shutter delay?
No, it is. It's there's a shutter open delay that was right up here. Get integer param, shutter open delay, and shutter close delay. And then this is where you acquire a frame. So if we were told to erase before the exposure, then do that. Wait for the exposure time. So where does it actually start the exposure? Here. Oh, there's nothing you do to tell it to start exposing. All you do is open the shutter. It's always exposing, right? And it's just an image plate. So you don't have to do anything to start the exposure. It's just that once you open the shutter, you start saying, you know, start my timer. You wait for the timer to get done, and then you close the shutter. And then you tell it to read out. Command scan, and then you wait for that scan data ended okay. So you basically open the shutter, wait, close the shutter, and then tell the thing to read out.
So a board here is getting the unique ID.
Is it? Okay, I don't guarantee I've implemented that. Yeah, because here abort, where is abort implemented?
Is
Okay.
asynchronous with the.
Well, no, here, if the exposure was aborted, return an error. And where did I do the, oh no, here's where the unique ID gets set. So I don't, right? I'm not incrementing it.
Oh, you are not?
No, because that, I just returned if we did an abort. There's a difference between a stop event and an abort event. Abort means I want to kill this acquisition and return. Stop means I want to stop this acquisition at this point, but I want to read it. In other words, I might have told it to collect for 5 minutes, but I've decided after 1 minute that's enough, and I tell it to stop, but not abort. It's different. And then this is the task, this is the thread that gets launched. That, you know, it's pretty simple. So it gets waiting for, it just does, yeah, it gets a start event. Depending on the mode, are we in erase mode or acquire mode? And then here's where we, you know, do the loop over the number of images, presumably. If the images counter is 0. This has got some funky indent. That's weird.
There's a still 4.
Oh, this is a 4. Oh, I see. That's just a long for statement. I got you. So the indent's okay. So it's looping over the number of images and basically probably just calling acquire here, acquire frame. Boom, 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 boom. This is the right. So if it's acquire and it's idle, send it a start ID. Oops, lost my stop acquire sends a stop ID. If it's a race, I don't know. So you can see just the logic of, depending on the state, and if you've told it to start or stop or abort, it does various things here. It doesn't have to do anything with float 64. The report function just does a little message and calls the base class. You should always call the base class report function. And the constructor, pretty similar to what we've already seen. Create the parameter. I think we're creating an epochs timer queue and an epochs, a few epochs events. Connect, okay, here's the thing where we connect to, this is connecting to the MAR345 DTB server. So one of the things passed to this constructor was the name of the server port. So this was a driv asyn IP port that was created earlier in the startup script connected to the MAR345 DTB socket server. So we passed the name of that port here, and then pasyn octet sync.io connect to that server port, giving it the address of a pasyn user pointer, and setting some parameters in the default parameters in the library, creating the thread that collects the data, and just the IOC shell stuff. And we didn't quite get done this morning with what I wanted to show you then, which was the, just quickly look at the Perkin-Elmer driver, which is a different type of driver using a vendor C API that supports callbacks. So we can just look at this quickly. This is the header file for it. It's redefines, and you'll see that the template file also redefines basically the AD image mode MBBI. So it does, remember, the one in AD base has, collect a single image, collect multiple images, or collect continuously. This one adds an additional mode here, which is image average, because that's something the vendor supports, where you can average a bunch of frames in their frame grabber. It uses their FPGA, so it's fast. You could use the plugin, the process plugin to do this, but it's probably faster to support it in their hardware. And also redefining what the trigger modes are in the base class. It's just internal, external. Here we're going to, have internal, external, free running, and soft trigger. That's the modes that they support for the trigger. And then these are some constants, time constants, and capacitance constants that have to do with their hardware. Some state that they support. I think that's, I forget actually if that comes from them or us. And right, so we basically pass it two things in the constructor here, which is the interface type and an interface identifier. They support a couple of different flat panel interfaces. One is this proprietary fiber. The other is truly GigE. And then, depending on which it is, you identify what detector it is you're talking to by this character string here. And so we got a in 32 and a float 64 and float methods. Those are the ones we redo from the base class. And then we've got a few callbacks that we've defined. So they can give you a callback at the end of every frame. They can also give you a callback at the end of an entire acquisition series. And so we support both of those callbacks. Then these are just the parameters, the new parameters that are Perkin-Elmer specific that we define. These are the index numbers for those. And then there's some private data that we won't go into details of all this stuff. Probably see it when we need it. And then here's some internal methods of that are to start and stop acquisition, acquire an offset image, acquire a gain image, load a gain file, and so on. These are the strings that correspond to the new parameters that we've defined. All the same kind of stuff we've seen before. So this is the configuration command and the the configuration command that's called from C. Here's the constructor, and just copying these model identifiers into these things, creating all the Perkin-Elmer specific parameters, setting default values for some parameters, create a thread that updates the images. So we didn't get away without having to create a thread at all, even though it supports callbacks. So we'll probably see why that is. So then we just call initialize detector here. I put that off into its own function. And let's see what this looks like. Okay, so here's where we've implemented an epochs at exit function here that it actually does call the destructor for the class, right? And that'll go through and presumably this is the destructor, so it calls acquisition close. That's a method in their library that makes sure we turn off the detector before we exit, and then free up a bunch of buffers that we have allocated along the way here. Initialize detector. So the first thing it does is these are methods from their, functions from their library. Acquisition enum sensors. So that tells them to go out and build the list of detectors that they found on the system. Those could be gigabit Ethernet ones. And let's see, if that didn't work, we return an error. Then it calls get next sensor here. And if that fails, it returns. So if it didn't find at least one sensor, it's going to return false. And now it's trying to find a gig E. This is in the case of a gig E. That's right. So this is switching on the type of detector. So if it's that's right. If it's one of these proprietary interfaces, we are assuming here that it's the one and only one that's hooked up. But if it's gig E, it goes and tries to find it either by its IP address or its MAC address or the name of the detector. So this is where it's trying to figure out if it can connect to it over gig E. And then here is where we're telling their library to give us callbacks on an end of frame and an end of acquisition. We want it to call us. Set the camera gain and the binning mode, the camera acquisition mode, so on. That stuff is commented out. This is, again, a method they give us to ask how the sensor is laid out, basically how many rows, how many columns, what's the data type, and so on. From that, we allocate the memory for it. And you tell their library to set data acquisition. I think we've built here one of these objects, and then we tell it that, and we're passing it a pointer to ourselves, because that's what it's going to use, presumably in the callbacks. And configuring the binning according to these parameters. They've got different ways of handling binning. In fact, I think they only support a few things. You can do like 1 by 1, 1 by 2. So it only supports a few different options. Let's see if we can find, this is the report function. So we're actually printing out a lot of stuff here out of their, basically printing out, if we ask for a lot of details, printing out a complete structure that they provide. Reporting on the sensors. Right. So this report sensors is called by report. There's a lot of debugging stuff here. Okay, so this is the callback that we get on the end of a frame. So it's calling get acquisition data, and then it calls the end frame callback. Oh, I'm sorry. This is the end frame callback C callable function, which then calls the class method here. And let's see where this is allocating the memory. So it's find the offset into the frame memory, blah, blah, blah. Anyway, I don't know, we need to go through this in gory detail. Here's the end of the acquisition callback in C, which then calls the method, the class method. And yeah, you can be acquiring here with the Perkin-Elmer, it needs frequent normalization. So you can tell it, to acquire a set of offset frames with no beam. You know, you turn the beam off and you say acquire 10 offset frames. It'll average them together and store that in some place where then their library will correct all subsequent frames for the basically the offset, what you get with no X-rays. It'll correct, it'll normalize to that. Got a write int 32 function, this kind of stuff you've seen, where we turn on acquisition or turn it off. Call set binning if we change the binning. If you can reinitialize the detector. So, you know, if somebody power cycled it or for some reason you need to reinitialize it, there's a PV to do that. Change the trigger mode, load the gain files, and so on. Write float 64, it only does anything if you change the acquire time, no, or the gain.